Which part of maths has got me waking up so terrified, you ask? Well, I'll show you the nightmare that I had. She ran. Branches tore at her skin, but she didn't stop. She couldn't. They were getting closer. 2 men hunting her through the woods. Ahead, she saw it. A wild river, its dark waters crashing violently. There was no way to swim across. But then, a light. There was a cabin with a little boat outside and only enough space for 2. She banged on the door and it creaked open, revealing an old man. "Can you take me across?" she gasped. "I can, but they're coming too. They've threatened me." Her stomach dropped. She wasn't escaping them. She was crossing with them. Outside, footsteps crunched closer. "There's a way, a plan, but you have to trust me." Did she have a choice? She was running out of time. What was his plan? Well, he's only got 1 space in the boat, but you can't leave the girl alone with a killer on either side where a single step would give her away. He decided he would take her across first, and then he would go back for one of her pursuers. As soon as he dropped him across, the girl rushed back into the boat and climbed back out on the original side. She then hid so the second killer could get in the boat and cross. Whilst they began to hunt her, the man went back, grabbed her and took her further down the bank, hoping that she'd get a head start before they realised. He then took himself home, hoping he'd escape the nightmare for good and ready to look into buying a nice property in the city, far away from these cursed woods. A problem that seems innocent enough. After all, it's just about crossing a river. But beneath the surface lies something far more sinister, a puzzle that leads straight into the heart of mathematical horror. You might have heard of it before. The one with the wolf, the goat and the cabbage? But these don't really capture how terrifying this problem really is. The old man clearly had a plan, but what was it? Well, we can break it down using graphs. By graphs, I'm talking about network graphs, which help us represent all sorts of things in maths. They're made of these points called vertices, which are connected by these lines, which we call edges. And this helps us show all sorts of different relationships. To solve our problem, we make all of our characters into vertices. We can then connect them with edges if they're not allowed to be alone together. Then we see that if we were to remove this top vertex, all of our edges would disappear. This means that we've covered the graph. And since we've chosen to only do that using 1 point, that's our minimum vertex cover. We could have chosen to get rid of both M1 and M2, but then we would have had a higher vertex cover of 2. So we know 1 is the least that we could have. Since our minimum vertex cover is 1, this tells us that we need 1 space in our boat to be able to complete the problem following all the restraints. Our next big question is, does this always work? The answer is unfortunately no, but I promise we did it for a reason. Say she had more people chasing her. Using the same method as before, we can still find our minimum vertex cover is 1. But let's see how this plays out. We can start the same as before, and we'll take the girl across first. Then we'll come back for one of the murderers and take him across. But then, when we try and bring the girl back like how we did before, we're stuck, because if she's dropped off and we pick up one of the murderers, she's still got 2 right behind her. 1 space clearly isn't enough for this problem. Fortunately for us, we can just use every mathematician's favourite trick and add 1. Now, if we had 2 spaces in the boat, let's see if that works. Our technique to take everyone across now is to keep the girl in the boat the whole time. So now we can see that everyone can get across as long as she's in the boat, and then our old man is still good to go home. No matter how complex the graph is, you know that your boat size is always either the minimum vertex cover or the minimum vertex cover plus 1. Okay, so now that we know it's one of these two options, we're safe, right? Not quite. The real terror is we have no way of knowing which is true. Okay, that's kind of an oversimplification. We know it's always one of the two, but we haven't got a mathematically sound way to know which without trying it. This is where the problem becomes horrifying, because it comes under a class called NP-hard. NP stands for non-deterministic polynomial time. For problems in NP, you can guess at a solution and then check that solution works pretty easily, but actually finding that solution, that's a different story. It could take minutes, years, or even until the end of time. It's like being trapped in a maze. You can guess which way to turn, and you'll know if you've got out, but whilst you're in there's no map, no guiding light, just endless dark turns. For a river problem, you might guess that the boat size will be equal to your minimum vertex cover, and you can check that, but there's no algorithm to predict whether it will be that or the minimum vertex cover plus 1. You just have to brute force it. This isn't the only NP hard problem. There are some fun ones and some less fun ones. Here's the twist. NP hard problems are all just as difficult as each other. It's one of the requirements for the classification. This means if you had a method to locate a solution for one problem, you could use that to find a method of figuring out solutions for any of them. It's a bit like finding the key to every locked door in a haunted mansion. Unlock one and you have access to all the others if you're brave enough to try. If you were able to find one of these methods and solve all of these NP hard problems, you would be well on your way to $1 million check. This is because one of the Millennium problems, as posed by the Clay Mathematics Institute, is related to the idea of NP, and they award $1 million to anyone who solves one of these problems. Everyone put on a brave face. We're going to get into one of them now. The question that's asked is, if it's easy to check a solution is correct, does that mean it's also easy to find the solution in the first place? So the main idea of the problem is P versus NP, where P stands for polynomial time and NP stands for non-deterministic polynomial time. The easiest way to explain what P and NP are is through thinking about checking and solving. So P problems can be checked easily, and so can NP problems. But the thing about P problems is that it's also easy to solve them. We can find the solution just using some kind of algorithm. Whereas, as we've said before, NP, finding the solutions is hella. A way to visualise this is using circles. So our orange circle is NP, which contains all the solutions that can be checked easily. P falls within this because it has solutions that can be checked easily, but also the solutions can be found easily. But if someone found a way to find a method to solve all of these NP hard problems, then NP problems would also be easy to solve, which would mean that these two circles are actually the same circle and contain all the same problems. If that's true, then we have P equals NP, but at the moment, we don't know. No one has found enough justification leaning either way. But if someone did find that P was equal to NP, it would revolutionise everything we know about computing mathematical problems. This Millennium problem is quite a young conundrum, officially established in 2000, but it's been torturing mathematicians for way longer. The idea of P and NP complexity classes came about in the early 70s with the rise of computers, but the original river crossing problem is still much older, from around the late 9th century in a manuscript called Propositions Adequendos Juvens, which is not a demon summoning spell, but actually translates to problems to sharpen the young. Mathematicians have been hunting for a way to solve these NP hard problems for ages, even before they knew there was a whole class of problems in this category. With the $1 million prize on the line, many have been hunting high and low in the darkest corners of the oldest crypts, but no one has found a solution and lived to tell the tale. So give it a try, if you dare.